Leadbeater possums are critically endangered and highly dependent on continuous canopy pathways to survive. Bushfires, climate change, and logging have removed hollow-bearing trees and opened dangerous gaps in their environment. When forced to the ground, possums are vulnerable to foxes, cats, and owls. Rebuilding elevated connectivity became the core challenge that this project aims to address. The design intent asked how an artificial canopy structure could safely guide possums across fragmented habitat. The aim is to create an enclosed, elevated tunnel that blends with the forest, offers protection for predators, withstands fire, and supports the possum's natural climbing and gripping behaviours. I collected references from wildlife crossings, rope structures, woven nets, and canopy bridges. These examples help me understand enclosure, material behaviour, and structural tension. While many wildlife bridges exist, few are fully enclosed or suitable for small, fast-moving arboreal animals like the leadbeater possum, highlighting a clear design opportunity. Concept A explored an open-form rope bridge suspended between trees. It allowed airflow and flexibility, but the open sides offered no protection from owls or climbing predators. This concept helped me understand the weaknesses of exposed structures and why enclosure would be essential. Concept B looked at a ribbon-style bark pathway. It visually blended into the environment, but lacked the texture grip possums rely on. It also didn't provide overhead protection. This concept emphasized the need for both camouflage and three-dimensional enclosure. Concept C introduced a mesh tunnel, which for the first time addressed enclosure and safety. However, it required improvement in material strength, fire performance, and anchor stability. This idea became the foundation of the final tunnel design developed later. Research during the Discover phase focused on understanding possum behaviour, predator activity, and post-fire forest conditions. Leadbeater possums avoid open spaces and depend on dense canopy. Predator mapping showed that ground travel dramatically increases mortality. These insights confirm that the design must create a completely elevated, protected route that aligns with natural movement patterns. This stage identified the functional requirements of the tunnel: a fully enclosed form, structural stability across long spans, materials that withstand fire, and textural surfaces that mimic branches. The structure also needed to be lightweight, safe for trees, and durable in extreme weather. User needs included enclosure, grip texture, predator protection, and a tunnel diameter suited to fast climbing. Environmental needs included low-impact anchoring, fire resistance, and a system that supports long-term canopy regeneration. These factors shape the core design criteria used throughout development. The develop phase explored different mesh densities, knot patterns, and tunnel geometries. Early sketches examined how the tunnel could sway with the trees without collapsing. Feedback emphasized fire-resistant materials, leading to the exploration of Kevlar rope. This stage refined the tunnel's circular form and the behavioral logic behind its enclosure. 3 different low-fidelity models were created to explore attachment systems, tunnel shape, and internal mesh behavior. Each model tested a different aspect: structural tension, entrance clarity, and overall stability. These prototypes demonstrated how the mesh responds under weight and movement, informing the structural direction of the final design. Using the implications wheel, I explored the broader impacts of installing a canopy tunnel. Benefits included improved survival rates, restored connectivity, and reduced long-term waste when using durable materials. At the same time, it highlighted risks such as entrapment, installation impacts, or environmental disruption if maintenance is neglected. These insights guided safer design choices. Further prototyping focused on refining knot spacing, entry geometry, and anchoring techniques. Testing revealed how different patterns influenced grip and how the tunnel reacted to sway and wind. This iterative process strengthened the design's reliability and ensured it supported natural climbing behaviour. Kevlar rope was selected as the primary material due to its fire resistance, tensile strength, and durability. Its woven texture provides natural grip for possums. Stainless steel components support the tunnel's shape, and tree-safe straps allow secure installation without damaging bark. These material choices respond directly to the environmental conditions of post-fire forests. This section outlines how the structural system is assembled. The tunnel is knotted into an enclosed, cylindrical form reinforced by internal rings. Camouflage wrapping helps it blend with surrounding bark. The modular designs allow repair or replacement of individual sections, providing longevity and reducing environmental waste. The storyboard communicates the full user journey. A possum encounters a burnt clearing, detects predators, discovers the Kevlar tunnel, tests the knots, moves through the enclosed mesh, and reaches new food sources on the other side. This narrative demonstrates how the design restores nightly movement and reconnects the canopy. The medium fidelity prototype tested the scale, mesh density, and structural form of the final design. The model demonstrated how the tunnel maintains its shape, how the knots support grip, and how the entrance functions as an identifiable safe access point. The final design is a fully enclosed Kevlar canopy tunnel that restores safe movement between trees. It protects possums from predators, withstands fire conditions, blends into the environment, and supports their natural locomotion. It is modular, durable, and suitable for installation in multiple forest sites, improving resilience and ecological connectivity. Following the double diamond allowed me to move from broad ecological research into refined behaviour-driven design. Discovering real threats reshaped my assumptions, defining needs clarified enclosure and material choices, developing prototypes refined form and function, and delivering the final design demonstrated how nature-positive thinking can meaningfully support conservation.